All right, now we're finally going to look at our last quantity, energy. And it's important to recognize that energy is not really natural in Newtonian mechanics. In fact, Newton himself didn't really have an idea of energy. Energy was really developed as a concept sometime later, first by Lagrange and then later by Hamilton, and really was best understood through the ideas of thermodynamics. Thermodynamics was really developed in the latter part of the 19th century and the early part of the 20th century. Um, so when we start thinking about energy, we're going to get pretty deep into the weeds when it comes to taking the calculations to sort of a new level. And a lot of what we're going to do today in this video is to look at some of the things that people have done in retrospect, taking the concepts of energy that were developed later and then applying them to Newtonian mechanics. So if some of the stuff that we look at seems a little bit abstract at first, that's really the reason, because again, energy is not a really very natural quantity within Newtonian mechanics. It's sort of hidden, and it really comes to the forefront in Lagrange's variations of classical mechanics, as well as the Hamiltonian, which is really where energy starts to become front and center in classical mechanics. So what we're looking at is the concept of work and energy. So what I want to first start with is, first of all, a one-dimensional system, because we're going to see that adding multiple dimensions makes things more complicated. We're also going to consider constant forces. So most forces in nature are not constant. They change, particularly with location. But nevertheless, we're going to assume a constant force, and we'll come back and look later at a force that varies with position, or a force that varies with perhaps velocity. But in this case, we're going to start with a constant force. We're going to deal with one dimension only. So things moving in a straight line, we're not going to worry about moving up and down. We're not going to worry about moving in and out. It's just left and right here. And we're going to think of the simplest system that we can imagine, that we've got a mass. And you can imagine this as sitting on a frictionless surface, so there's no friction. You can also imagine this as being out in space, so there's no friction and no gravity, no other forces acting, just this constant force. That's the only one acting on the mass. And we're going to apply the constant force, and we start the constant force with the mass at position x1. And of course, if we apply a force is going to be equal to some mass times an acceleration. So if this is the only force acting on the mass, it's going to start to accelerate. And we continue to apply the constant force, so we're still applying the constant force here, F, up to the position x2, and then we remove the force. So basically, this is kind of like pushing on something and then stopping. You could imagine maybe an ice puck in hockey, and you're pushing on the ice puck for a few inches, and then you pull the stick back and you watch the ice puck go flying off. So you're applying the force between positions x1 and x2, and that's a displacement called delta x, which is defined as x2 minus x1. Initially, the velocity is 0, so we're going to call v1 0. So the velocity at position 1 is 0, and the velocity at position 2 is some v2. So there's a delta v here. So clearly, we've applied a force through a certain distance or through a certain displacement, and it has resulted in a change of the motion of the system. So initially, the motion was 0, the velocity was 0. We've had an acceleration, and now we have a new velocity, and it's going to move off at that new velocity in perpetuity, unless some other force acts on this mass. So what we're going to do is we're going to define a quantity called work. And we're going to say that the work is equal to the force times the distance that the force was acting. So the force started acting on the body at position 1, and it stopped acting on the body at position 2. So force times the difference in there, the displacement during that position, is what we're going to call work. And our job is to figure out, what is this? Does it have any special significance? Is there anything, any way that we can relate this work to this change in velocity or to the new velocity? So a couple things to point out here. We're dealing with a constant force, which means a constant acceleration. As long as the force is being applied, the acceleration is constant. So there's a couple things that we should know, that for acceleration being constant, the instantaneous acceleration is equal to the average acceleration. The acceleration is the same all the way throughout. So the acceleration at any given moment in time is going to be the exact same as the average acceleration because all accelerations are the same. They're constant. And then for a system that's under constant acceleration, the average velocity is just the velocity at the final point plus the velocity at the initial point divided by 2. So let me just graph this really quick, and then we'll have to erase it because I'm going to need this space. But we can imagine that as time increases, the velocity initially starts at 0. So this is velocity 1. This axis is the velocity axis, and it's going to go up like this. And here, this is velocity 2. This value here is velocity 2. And then all this is saying is that if we have constant acceleration, which means the velocity is going up at a steady rate, it's not jumping up and then plateauing off or staying at a low value, then jumping up really high at the end. It's going up at a steady rate. The average velocity is just going to be halfway up this thing. So this here, this v is going to be halfway up this, and that's going to be the average velocity. And so that's just going to be v2 plus v1 divided by 2. That's halfway up this slope. So we're going to need these very shortly. So I will erase this again because we're going to need this space. So the question is, can we derive something from this expression that will relate velocities to this idea of work? All right, so let's do that. So the first thing we're going to use is we're going to invoke Newton's law, which is that F equals ma. So in this case, we're going to have that F is equal to the mass of this body, whatever it happens to be, times the acceleration, and then that's going to be multiplied by the displacement, the change in x position. The next thing is to recognize that, again, for an acceleration that's constant, the acceleration is the same thing as the average acceleration. So the average acceleration, this is going to be mass times the average acceleration times the change in the position. And this is where things get interesting because the average acceleration is defined, and you can go back and look at the original video where I talked about in Newton's first law and defining what acceleration is. The average acceleration is just the difference in velocities between 2 points divided by the time between those 2 points. So we can rewrite this whole expression. We can rewrite this work is going to be equal to the mass times the average acceleration. Well, what is the average acceleration? It's the velocity at this point minus the initial velocity, which in this case is 0, but it doesn't have to be 0. We're just using 0 as an example. It could be a different value, divided by the time between these 2 points. So that would be the time at when we stopped applying the force minus the time that we began applying the force. So that's just the average acceleration. That's just this equation here. And then we have a delta x, but we already know that a delta x is just x2 minus x1. So we're just going to have x2 minus x1. Now, this is just standard multiplication. No vectors here. All this is scalar stuff. So we'll deal with vectors later. But for now, we're just working with scalars because we know how to deal with scalars. And it doesn't matter if we divide here or divide here. We can take the denominator here and move it over. And that's exactly what we're going to do. We're going to say that this is the mass times v2 minus v1 times now x2 minus x1 divided by t2 minus t1. Again, it doesn't matter what order we do the division in. We can do the multiplication, then the division, and then this next multiplication, or we can do multiplication, multiplication, and then the division. That's a property of multiplication and division that the order doesn't matter. So now if you'll notice, this thing here is just the average velocity. This is just the average velocity. It's x2 minus x1 divided by t2 minus t1. That's the average velocity. So once again, we can rewrite things. We can say that the mass is going to be velocity 2 minus velocity 1 times the average velocity. Okay, well, the average velocity is also, as we've seen, v2 plus v1 divided by 2. Notice what I'm doing here. I'm trying to get rid of these x variables, and I'm trying to get everything in terms of v's, v2 and v1. So the average velocity is just take the final velocity and the initial velocity, add them together, and divide them by 2. It's just a standard average. So what I can do is rewrite this one more time as m is v2 minus v1. And then we would have here v2 plus v1 all divided by 2. All right, so again, I can do the multiplication and division in any order that I want to. So I'm going to pull the 2 out. So let's write this as 1/2. So the 2 is the first thing that we're going to write. And then we have the mass. And what we can then write then is just this v2 minus v1 times v2 plus v1. All right, so let's FOIL this out. If you remember your algebra days, first outside, inside, last. Let's FOIL this out and let's see what we get. We get 1/2 the mass times, what do we get? v2 times v2, that's v2 squared. Then we get v2 times plus v1, that's plus v1 v2. Then we get minus v1 times v2, that's minus v1 v2. And then we get minus v1 and plus v1, and that's minus v1 squared. And we have a plus v1 v2 and a minus v1 v2. Those two cancel each other out. They're opposite, so they add to 0. And so what we end up with is 1/2 the mass. Now the mass, we can bring this in. We can distribute this in. So we end up with velocity 2 squared minus 1/2 the mass times the velocity 1 squared. So this is something interesting. We have two quantities. They're not exactly the velocity. They're the velocity squared multiplied by the mass and divided by 2. But we have two quantities. One, this is in the initial state, or excuse me, the final state of the system, and this is in the initial state of the system. So what we can do is we're going to make a definition. So let's make a new definition. I'm going to make this definition up here because I'm running out of room. We're going to call it T, which there's lots of different symbols used for kinetic energy. You could call it KE, you could call it E sub K. I'm going to use T. That's a standard symbol in modern physics for kinetic energy. I'm just going to use T because it's the simplest and fastest one to write. And we're going to make this definition that's just going to be 1/2 the mass times the velocity squared. And so this would be 1/2 the mass times the velocity times 2 squared. So that's going to be equal to T2. And then this is minus 1/2 the mass velocity of times the velocity at position 1 squared, and that's just going to be minus T1. Okay, and that's going to be equal to delta T, which is the change in the kinetic energy. This will be the change in kinetic energy. So what we have actually established at this point is that the work is equal to the constant force times the displacement. But that's also equal to the change in the kinetic energy. And this is called the work energy theorem. Now, we've only proven it for constant forces in one dimension. So we'll have to figure out how to expand this. But this is still the basic idea of the work energy theorem. And that is going to be extremely important in archery, because what this says is that any work done is going to result in a change of kinetic energy. Or another way of reading this is that a change in kinetic energy is going to result in some work being done. So we're going to see that the work of penetrating an animal is defined or quantified by the change in the kinetic energy. In this case, for the case of archery, that will be the change in kinetic energy of the arrow. But we're going to have to do a little bit more work to get there because we really want to understand the work energy theorem for non-constant forces, for forces like friction or drag. And we also want to understand it for non-one-dimensional systems. So systems that involve multiple dimensions, which means we're going to have to work with vectors instead of with scalars. So we'll see how this work energy theorem gets reconstituted and what it looks like for more complicated 2+ dimensions and instantaneous forces.